So thank you guys very much for coming. This has actually been a workshop that Uri and I, Uri's just leaving, but you're welcome to say hi. He's the organizer of this event. Uri and I came up with this workshop about, say, a year ago when we worked together. We thought it would be awesome to have you guys come over and learn just like the basics, just like have an end-to-end kind of run with machine learning. Basically get the data, clean it up, extract some features, train a model, test it, deploy it. It's gonna be awesome. So actually seeing this idea materialize today is awesome. So thank you guys very much for coming. Just so I'll know you guys better. How many of you have some experience with Python, written Python code? Oh, awesome. Analytics, how many of you held analytics jobs? All right, great. So just a quick introduction. My name is Zehori. I'm a data scientist. I'm a team leader at Bigabit. At Bigabit, what we basically do is we help huge brands, usually game companies and app developers, to acquire new users and retarget old users. So basically, if you want to acquire new users in the country that you're working in, or you want to expand to a different region, so basically what we do is we use machine learning to segment the audience and target and help you guys understand and target those like the users that will be of high value to you. That's in a few words what Bigabit does. So the agenda for today, what we're going to talk about. So what we're going to talk about is basically what is machine. This is machine learning 101. So what is machine learning and why we need it? We're going to get into the difference between classical programming and machine learning, and basically why do we need it? Generic machine learning workflow. So basically, how do you go about doing this machine learning thing? The steps of machine learning. So this is like a breakdown of the workflow. So we're going to get into each and every one of these. Ishay is going to take over on the feature engineering part, and then we're going to get to work. This is the reason you guys came here. All right. So what is machine learning and why we need it? So basically, machine learning is a subfield of AI. It's basically you wanna get the computer to learn and improve from experience without being explicitly programmed. What does that mean? In classical programming, what we do is we put in data and rules, and we get answers. An example of that would be if some number is greater than 15, we'll do that, right? Else, return something else. Machine learning had kind of flipped the process. What you do is you get data and you get answers, and you put in data and answers, and you extract rules. So what is that? How would you program in a classical scenario, a program that would tell you whether or not a picture is a picture of a banana or not? Like that's a little bit more difficult than saying whether or not a number is greater than 15, right? You got to put in a bunch of photos, and you got to tell the computer, this is a banana. And eventually the computer is going to figure out the set of rules that make a picture be a picture of a banana. So it's going to find some pixels, and it's going to say the dominant color is this, and it's going to say the edges are a bit curvy. This is extremely difficult in a classical programming scenario, and this is why machine learning was invented in the first place. So the problem that we've talked about now is a problem of classification. We want to say whether or not something is a banana or not. But the realm of machine learning is much greater than that. So in machine learning, we have, this picture tries to capture the whole thing, but it captures a glimpse of it. So basically what we have is this realm over here of unsupervised learning. Basically what unsupervised learning means is that we don't know the correct answer. We have a lot of data. We can tell you something about, we have features for the data. Basically we have rows and columns. We can have many rows and many columns describing something. But we don't know exactly what this thing is. So what we want to do is we want to maybe cluster together rows that are similar or that are close in the Euclidean space. An example of that would be grouping together of documents. So basically, if you have a whole bunch of documents and you know the text of them, and you want to group them together and say, these documents all are medical documents, and these are all legal, and these are all whatever. So basically, you use unsupervised learning to do that. And then you can be saving a lot of human effort to tag everything. Because you have all these, you just tag a little bit, and then you say, all of these are close together. So you can extract a lot of information from that. The other scenario is supervised.
Yeah, but you still have to classify the groups.
Yeah, so the thing is, yeah, but you don't have to classify the whole thing. Yeah, you just have to classify a sample and then say which ones are closer together. Right? The other realm over here is reinforcement learning. There's a field that had gained a lot of momentum lately. AlphaGo, you guys know AlphaGo? Yeah, beat the world champion at Go, a super complicated game. So what is reinforcement learning? Reinforcement learning is learning by just having the computer not giving it any data, just letting him figure out for itself, like a baby. You send we call it an agent. Send an agent to the world and it makes mistakes, and it learns from its own mistakes. It does random stuff, so it bumps into a wall, and then it figures out that there's a wall there and it can't go through. So an iRobot would be a good example of something that explores the space and then figures out for itself. An iRobot doesn't have a data set of the room that it cleans, right? It just figures it out for itself. And the last but not least, this is the most, I reckon, popular field of machine learning. This is what we're going to do today. It's called supervised learning. So supervised learning meaning you have a data set and you have the answers, and you want to figure out the rules. Right? So an example of that would be the Titanic competition that we're going to do today. So basically, we're going to classify whether or not a person had survived the crash of the Titanic or didn't. And we're going to do that by examining the patterns that emerge from the data. So we have all the people on the ship and how much they paid for the fare and what class were they in and what floor on the ship were they in. And then we're going to figure out whether or not they survived. Another type of supervised learning is regression. So basically, if we all, we want to purchase a house, say, and the house has this and this many bathrooms and this many bedrooms, and it's located here and there, we can use this data to estimate the price. It's not a 1 and a 0, it's not a classification, but it's a price, it's continuous. So we're going to say this house is going to cost, I don't know, $500,000, $100,000. And we're going to give rough estimates of how much the house is going to cost us. That's the output of a regression test. And this is where we're going to be today, where the arrow points. Classification, as I said, the Titanic. So let's try to kind of describe in broad brushstrokes the generic ML workflow. So you get a data set. We're going to talk about data collection in a bit, but you collect data, and then you have a data set that's rows and features. And then you prep the data. What do you mean prep the data? You prep the data for analysis. You make sure the data is clean. You make sure that all the features are transformed and are in scale. You make sure you extract features that might be meaningful to the task at hand. And then you go to training the model. Then basically you build a model. You use a train and a test set. So you input this data in, and you input the answers as well. And then you go to the testing part. You see how well did you do. If the model only said, this guy's going to survive the Titanic, but most of them didn't, it's not going to be a great model, right? It's worse than random guessing. So this is an iterative process. You train and test, and you train and test. Eventually, you get a good model. Then, when you have a good model, you deploy it and have some system serve it. For example, you have a recommendation system, and you work at Netflix. You want to be able to deploy the model to bake it into the product itself for it to actually generate recommendations in real time, right? So this is inference. Actually doing the inference after you have baked the model into the product is the final stage. Then it's a loop. Then you get data, and you train it again, and you deploy it. That's what data scientists do in the real world. So let's talk a bit about data collection and how important that is. So basically, there's a saying in the machine learning world. It's garbage in, garbage out. And it couldn't be any more true. Basically, think of a model as a thing, an entity, that only views the world through the data it's given, right? So it's not like you and I that we see a picture of a banana and we say, yeah, this banana is a bit weird. I don't know why. It maybe has a lot of black spots. I don't know, or it's like greener than a regular banana. It doesn't have that. When you tell a model that this is a banana, its world composes of that banana. So it's going to classify weird bananas as bananas and regular bananas as not bananas, right? So what data goes into the model is the most important thing in machine learning, basically. Everybody's going to talk about modeling, and they're going to talk about deep learning, but actually what goes in, what features go in, is the most important thing. Another thing to pay attention to, and the realm of statistics deals with this a lot, is what am I not seeing? So the data coming in might be collected from, say, a poll, right? They call you up, election day, who are you going to vote? Who are you going to vote for? And most of you, 95%, 99%, just hang up the phone or say, this is not convenient, or I don't want to answer. But the people who do answer polls might be biased in some ways, right? They give answers, and you go ahead and analyze those answers as if you've gotten them randomly from the population, but they might be biased towards people that tend to answer polls. Maybe they're older, maybe they're younger, maybe they're more female, more male, I don't know. So biases in the realm of machine learning and garbage in, garbage out is the key takeaway from this. It's extremely important to pay attention to what you're not seeing and make sure your data accurately represents the problem. So talk a little bit about data QA, and this is a topic that's too often overlooked. By saying garbage in, garbage out, this is basically what I mean. This is like a drill down. Many times you see in data sets things that cannot exist, right? You see, I gave here an example that the state is New York and the city is Los Angeles. This doesn't make any sense. This data point is corrupt. And like we said earlier, the model in the scenario of Bigaboo, we see a lot of, maybe we might see someone that installed the app but did not click the ad, which makes no sense. You got to click and then you have to install. So basically, showing the model this, it would not question your data. This is its world. This is what it knows. And if you put in something like that, you got to be super careful to filter out things that are nonsensical in your data. Otherwise, your model is going to mess up its predictions. The other part of data QA is statistical QA. And this part is a bit more subtle. So basically in every job interview, every scenario in which you are tested or compared to someone else, people would evaluate you on your ability to question everything, right? You're given a data set, don't believe it. It might be filled with lies, and models trained on that might be performing worse than random because it's filled with biases and it's filled with things you got to sieve out in order for the model to work correctly. So basically, let's take this example. You got to be suspicious of overrepresentation of the population of Chicago, right? This wouldn't come up in a scenario in which it's not nonsensical. I mean, it makes sense that Chicago would be I don't know, bigger than Los Angeles in this data set. But you got to ask yourself, why? Why is my data biased towards people from Chicago? Why am I getting more data from there? This might bias your data set in ways that might go back and bite you later. Now Ishay is going to take the floor and talk about feature engineering.
Hi. So first of all, a few words about myself. My name is Ishay Telavivi. I work in a startup company named OptimalQ. In OptimalQ, we predict the availability of users, of customers, so that the organization can call the people who are available, and that will, of course, eventually will improve their answer rate and the conversion rate. Okay, so we were on the step that you had the data, you collected the data, you made all the QA and cleaning, and now you want to build a model and use the data. So the first step I'm going to talk about is feature engineering. And feature engineering, before we talk about what is feature engineering, let's just make sure that everybody understands what a feature is. So a feature is a single metric that goes into the model as an input. As you can see, the output is the level. Okay, it's 0, 1, or survive, or did not survive. But we have the input, and the input is composed of features. So gender is a feature, age is a feature, wealth is a feature in this example. This is only to make everybody on the same page. Okay. So feature engineering is actually a process where we modify the input that goes into the model. Okay, we add features, we subtract features, we change, we modify the features in order to get better performance of the model. Some people would say that this is much more important than the actual algorithm that you use. And this is very important. I mean, you can take any data set and just feed the model, you get a performance, but normally without feature engineering, you won't get good performance. Now, where do we get the features from? Okay, what is the source of the features? So first of all, it's from our data. Okay, you can take a single feature and we can modify it, we can change it, we can make some operation on it. We'll see an example on the next slide. And of course, we can take more than one feature from our data. Let's say we take 2 features, but one is a start date, and then we have an end date, and when we can have the duration as a new feature. And of course, we can bring new information from other sources if we feel that our data is lacking, is not bringing us any good performance. And as Ido said earlier, machine learning is an iterative process, and once we came up with a feature, we cannot, just collect a bunch of features and boom, try them on the model. We need to verify that the feature that we are creating is good enough. So basically what we do, we generate a feature and then we evaluate it on the model, and if we see that it is, it improves the model, then we can update the model and carry on, because not every feature that we generate is good for the model. Any questions so far?
So how do you know which features are good and which features are bad for the model?
You test them, okay? You come up with a feature and you evaluate it. Okay, we'll talk about...
Value. Predictive value? I mean, if they can predict results, or how do you...
Yeah, you look at the results, you look at... we'll talk about metrics in a moment, but you're trying to see on the test set what kind of performance you get. If it improves your performance, you'll use it. If it's not, you won't. Okay.
Yeah. Does feature engineering maybe will give me biased answers in my model because I'm taking only what makes it good for my model?
We'll talk about it in the next 2 slides, because you want to test your model on new data. Okay. We'll talk about test set and train set and how to combine them. Okay. Yeah.
Question. How do you avoid, by selecting different features, how do you avoid what they call in statistics disturbing parameters like you can always find, there's always that story that you can find a connection between mathematics grades and shoe size, because you test kids at the age of 3 and kids at the age of 6. So there are some features that may be disturbing. They may look well, but they may look as if they contribute to your model, but they are just disturbing because.
Okay. Sometimes you can have a good feature, but if you have, for example, another feature that is correlated with the first feature, they will not work together. Okay. So a lot of things is just to try and test. Okay, I don't know if I understood the question, but
More or less.
okay. Sometimes a feature that you generated will not work well, but only with another feature, both of them will give you a result. Let's see some examples for feature engineering. This is really some small examples because it's a very vast field here. So the first is categorical features. Categorical features are features that are not numeric features. Okay, they come in category. For example, we have a feature here, named color, and the categories are red, yellow, and green. So what we do normally is we use one-hot encoding. Does anybody know the one-hot encoding? Okay, one-hot encoding. What we do here is we take each one of the categories in the original feature, okay, and we generate for each one of them new feature. So if we had the categories red, yellow, and green, so now we have new features, red, yellow, and green. Each one of them gets its own feature, and we have one, okay, for the right row.
Why is it better than just giving, let's say, red 1, yellow 2, green 4? Just give it a number.
Okay. Instead of 3 columns, you want 1, 2, 3?
Yeah, that's right.
Because the model gets numbers. That's what the model knows. And when you give it numbers, so 3 is greater than 2, 2 is greater than 1. But that's not the case with colors. I mean, red is not greater than yellow, for example. Okay? So you can give it.
You can say wavelengths, but yes.
Okay. Sometimes it's possible when you have, for example, if you have ages. Okay, you have a child, you have an adult, and you have an old man. So in that case, you can do that. Okay. So this is one example. Another example is timestamp features. When you get timestamps includes the year, the months, the dates, the hour, and everything. So you can extract a lot of information from that. You can extract the day of the month, the day of the week, the hour, a lot of things. As we talked before, okay, if you have 2 timestamps, you can have the duration, you can have trends, arithmetic operations, everything that you can imagine, subtraction, multiplication, and everything. Another example is bucketing or classification. Like we have the example that we have here on the right-hand side.
How an arithmetic operation is a feature?
No, it's not a feature. It is something that you apply in order to get new feature. Okay, on a feature or on a set of features. Okay. So a bucketing, some models would take bucketing better than an original column, an original feature. So for example, age. Okay, this is the example that we have here. So instead of age, we have buckets of ranges. Lower range, middle, and higher range. Another example is text analysis. Sometimes you will have, in addition to numeric features, you will have some text feature. Let's say, for example, comments, and you would extract, some insights, some words, some phrases that you have in the comment in order to create a new feature. And the last example here is called dimensionality reduction. and this is something that we use in order to get fewer features. For example, if you have a vector of let's say 10 numbers, and then you have for each number a feature, then you can use dimensionality reduction in order to squash it into I don't know 2, 3, 4 features. We're not going to talk about it too much, but models with limited number of rows of data, they don't like to be very complex. So the more complex the model is, the less performance we get. Okay, so this is dimensionality reduction. Any questions about feature engineering?
But bucketing, it seems that it can lead to not so good results. I can assume that if it's not for ages, for example, if you take a big bucket or a small bucket, it can highly change the performance, I assume.
It may lead to biased results, maybe.
Yeah.
It can happen, okay, but it very depends on the data, it depends on the model, okay?
What type of things will you use bucketing for? It's that age.
Any numeric feature that you can imagine.
Income, salary, instead of having something that go from 10,000 to 100 to divide it. Low, medium, and
It doesn't always work, okay, but this is something that you can try. Okay, now a few words about splitting train and test. We'll talk about how to do it in a while, but let's say why we do it. Normally, we take our data set and we split it into train and test. But what would happen if we let our algorithm learn our data, okay, the full data, okay, as we can see here, and then we take out the label and we ask the model to predict the same data. Do you think that we'll get good performance?
Yes. You get good performance for that data.
Yes, of course we'll get very good performance because our model already knows all the samples. You know that for the first sample it's get 0, and then it won't be a problem. But what would happen if we get it, if we let it predict new data?
Depends on data.
Depends on how good your model is.
Yeah, I think it's very tempting to say that the performance will not be good, but actually we don't know, okay, because we haven't evaluated it correctly. So what we do basically is split our data into train set and test set, and the model learns on the train set and we evaluate it on a test set, where the test set is basically represents new data, okay, data that the model doesn't know. A bit more sophisticated way is to split it into 3 sets: train set, evaluation set, and test set, where the model learns on the train set and we check it on the evaluation set. For example, if we add a new feature, as we talked before, we will examine it on the evaluation set. Why do we do that? We do that because we don't want the model, okay, to see too often the test set, because we want to leave the test set as something that, okay, represents new data. Okay, and of course, in addition, there is something called cross validation, where we use the test set not as something fixed, but we change it within the data.
How do you choose the size of the train set, evaluation set, and test set? How do you choose which part of the data?
There are some best practices, okay, but normally depends on your data. If you have a lot of data, okay, you will expand the test, because normally you want to have a lot of train set, okay, because you want to learn a lot. Yeah.
Can you explain more about the cross validation?
Cross validation? Yeah, cross validation is when you take your data set and you split it into a few folds, for example, 4 folds, okay? And then each one of the folds is actually serves as a test set on its turn. So you learn on the 3 parts, okay? 3 parts, you make the test, and then you test it on that part, and then you change it. So this way you can test all of your data. The reason that we do that is that we don't know if the test set is
Accuracy. It's accuracy
what?
to increase the accuracy.
It's not about the accuracy, it's about the variance, okay? Because I don't want to get into too much into it, but the test set is just samples that we don't know if they represent all of our data, okay? Maybe we get good performance, but the good performance will be only on that test set. So if we change and we test all of the folds, then we can have a good evaluation.
In the cross-validation, do you train everything from the start on each fold, or do you retrain a pre-trained model?
Not sure I'm following the question.
In cross-validation, you have several folds that you said each fold represent a training at a different step, a test at every step. Do you take a model, train once, test once on every fold, or do you take the model that was tested on one fold and change it, not start from the beginning?
No, you don't change the model. You take the same model
and retrain it from random, or retrain a pre-existing model? That's the main question here.
No, you train it from scratch, okay, and then you take the mean between the folds, between the test performance.
So that means that you have several models. That you have a model for each fold.
Yeah, actually, you call it a model. Yeah, okay. You have a performance per fold. Okay. The model is the same. You take the model and you make like 4.
The models might not be the same.
Yeah, but you want to keep the same parameters because this is what you're testing. You're testing these parameters. Okay. You don't want to change it. You're just making
the inner parameters that came from the training of the model might be different for each training step, for each training time.
Basically, what changes between the folds are the data. Okay. Normally not the parameters, but the data changes.
בדאטה מסוים שבחרת, כי הוא מחלק את זה סתם, ואז הוא לא יודע אם הדאטה הוא מאוד מתאים או פחות. זה מקטין את התלות בדאטה.
Let's discuss it later, okay? Okay, models. We're talking about models. 2 models we're going to cover. These are very basic models. The first one is K nearest neighbors. This model basically, what it does, it's take.
Supervised.
We're talking, as Ido said, today we're talking only about supervised learning. K nearest neighbors, basically what it does, it takes a sample that we want to predict, and it looks around on the closest samples, and according to the majority of the samples, it determines the class of that sample. We have here blue and we have red dots. Okay, this is the training set, and the yellow one is the one we need to predict. So we take, in this case, we talk about the K. We take 5 closest samples, and we see here that the majority out of the 5, 4 are red. Then this is the red that we will assign the green one. Okay, basically it's very simple, it's very intuitive. K, what is K? When you say K nearest neighbor, K is the number of the closest neighbors that we choose. What would happen if we take a different K?
How do they find close?
Good question. just wait 1 second. If we take 3, okay, k has 3, what will we get? What kind of class? Still red. Okay, what if we take 1? Okay, in this case we'll get blue. How do we select the k?
You train for a lot of cases and choose.
Yeah, we try and evaluate it on the tests, on the evaluation set. Okay, now you asked, okay, how do we measure? Okay, what is nearest neighbor? What is near? So in machine learning we have many types of measurement metrics. Some of them, or 2 of them, are here. A Euclidean is just you know, the standard metric. It's like you know, the Pythagoras theorem that we studied on high school. And then we have, for example, Manhattan, which force us to go, you know, on the lines.
Excuse me? If the characteristics, the sparsity, for example, if you go back to the k nearest points, between the training set and the test set would be different, then you can find very good number, very good k, and it would be meaningless for the other, for the test set. I mean,
what you're saying?
Assume that the sparsity or the characteristic of those points are pretty much the same.
What happens here? I will answer your question not in a direct way. What happens in this algorithm that on the training nothing happens. The algorithm just saves and remembers the location of the samples. Mm-hmm. Okay, everything happens on the test, mm-hmm. on the evaluation. What happens on the evaluation? For each and every sample, the algorithm takes the distance to all of the samples, okay, and then it chooses the k, okay, the k that requires.
And then you get a new set of data. You cannot predict anything because it looks different.
No, each one of this new data, each sample in the new data, will get its own prediction, but based on the same data set, based on the same training set. Okay? I don't want to, you know, there's a lot of things that we can say about pros and cons, but I will say only one thing. This relates to the point I have just mentioned. This model, when you want to predict, it takes a lot of time, okay? It takes a lot of time because we need to measure for every test set all the distances to the training set, to each one of the training set samples. Another basic model is called decision trees. Decision trees, it's simple, but it's very important because many other relevant and popular models like random forest, like boosted trees, if you have heard of, like XGBoost, they use it. Basically, what happens in this model is that on each step, the model takes a decision how to separate the data, okay, how to cut the data in a way that they will have full separation. What is full separation or maximal separation? It means that if we separate the data, we get a majority of one class in one side and another class on the other side. Let's take just 2 extreme examples. If I split the data and I have, let's say I have boys and girls, and on one side I have 100% boys, and on the other side I have 100% girls, then I can say that this is full separation, and this is very good for the model because the model can make the distinction between the classes. Okay, if I make this separation and I see the same percentage of boys, on that case I will not be able to learn. Okay, this is not a good separation. So what happens here, okay, in this diagram is that on the first decision point,
the model takes the income as the feature to separate with on the T1, and then we can say that we have the majority of red on the right hand side, and we have the blue on the left hand side. Okay, I will move on because just to present the basic. Of course, on each and every decision point, then the algorithm continues to split each and every branch of the tree. Okay, this can also be separated in case we have, okay, two of the classes on the same side. As I said, this is very intuitive and explainable algorithm, and we can learn multi-class problem with that, but it is prone to overfitting.
Well, so we can only really show something that you already learned. But if something is presented that is new, that you will not be able to handle it. Tree-based, right?
No, it does learn. It does learn.
Something that they will see in the train set, you won't be able to predict it.
It will be able because it has a rule. What the algorithm does in this case, the algorithm creates a set of rules, okay? And then let's say we get a sample. Okay, let's say we get a sample here. So the model asks, is income greater than T1? Here? No, it belongs to this branch. And then the second phase is this decision. Is it greater than this line? Okay, the depth or smaller. And then according to the decision points, we get to the location of our sample, then we can make the prediction. Okay? Okay, now for the last part of this presentation, before we go into the practice, just talk about a few metrics, only the basic metrics for classification, because there are much more metrics than what we present here. The first one is accuracy. We have this metrics here, and I want to present it in a simple way because the metrics is simple, but many people also experience one. Sometimes, you know, they tend to confuse here. So we have the columns. The columns relates to the actual. What is actual? It is the what happens in the real world, what happens in the label. Positive, we are going to talk about the Titanic. So positive here, and negative means if they really survived or didn't survive, the people on the Titanic. So everything here, both this one, this cell and that cell, it's about people who survived, and here it's about people who did not survive. Okay, this is the actual. We have the predicted, okay, on the left-hand side, that has positive and negative. This relates to our prediction, whether we say if the person or sample survived or not. So what we get here is true positive. True positive is we say that it survived, and it actually survived. We say that true negative, we say that it did not survive, and it did not survive. Okay, this one are maybe easier. False positive and false negative. False positive, if you remember, belongs to the negative. Why is that? Because the negative, it means that it did not survive, but we predicted it will survive. So it's a false about our prediction. Okay, we had false prediction, we said it was positive, and the false negative, it's actually other way around. We said this would be negative, but it actually positive, it survived. For those of you who come from statistics, okay, this is normally, let me just see, actual, this is alpha and this is beta, okay, in statistics. So, what is accuracy? Accuracy for us, the measure accuracy, if we take only the green ones, only the samples that we were correct on, divided by the total samples. Okay, this is a very basic metric. We can see an example here. Okay, let's say that these are the samples. We have seven samples. We have actual. Actual is the real world, whether they actually survived or not. And we have the prediction. And here you can see the false, true positive, false negative, and so on. And on the blue dots here, we can see where we were accurate, whether we were accurate on the positive or on the negative. And we see that we have 4 out of 7 accurate. So this was the first metric, accuracy. The other 2 metrics are precision and recall. Precision, sorry, we'll start with the recall. Recall is the measure, the metric that takes the real world, the real positives, and trying to take the percent of how many we manage to detect. Okay, if we have, let's say, 10 positives, okay, we're talking about only about the positives. Look, we have 10 positives and we manage to detect 2. Okay, so we have 20% recall. The other one is precision, and precision does not relate to the actual, but relates to the prediction, whether or how many of the samples we were accurate about. So we take the true positive, okay, the positive that we were right about, and we divide it by the total prediction. Okay, and earlier it was true positive also, but divided by the total positive, real positives. Okay, we can see an example here. We have recall, we have precision. Okay, look, these are the same places, but we divide it by different numbers because we have 5 actual and only 4 on the precision. Yeah.
Can you give like in one sentence for each what use case for different metric?
Yeah, for example, recall, when you use the recall, when you want to really detect, as it says, you want to detect the positive. For example, okay, in the bank, you want to decide whether to give a loan to a customer. So you want to detect these, suspicious people.
Okay, so why is positive is more important than negative in that case?
Because you don't mind to get someone, who is, someone in between, okay? Okay, you want to get all of them. You don't want to miss anybody. You don't want to not detect someone, okay? Last thing here is the confusion matrix. Confusion matrix takes all of the classes, okay, and you have it on the columns, you have it also on the rows. These are the ones that you predicted. This is the true. And of course, on the diagonal, you get all the accurates, all the, no, they're all positives. For each one of them is the positive. But yeah, you get the true positives, okay, in the diagonal. And then you can see here all the ones that you missed. And you can calculate the precision, okay, on this axis. You can calculate the recall on that axis. This is something very confusing, you see, as it says, as the name. So the confusion matrix. Normally, it doesn't have it here. Normally, we need to write whether this is the actual and this is the prediction, because sometimes you will see it other way around. Okay, so let's start working.